Welcome everybody to Algebra 2, Section 3.5, Vertex Form of Quadratic Functions and Inequalities. So we talked last time about standard form of quadratic functions, and standard form, let me remind you, was f of x equals ax squared plus bx plus c. Vertex form is a little bit different. It is f of x equals a times the quantity of x minus h, quantity squared, plus k. Notice we have a, h, and k again, which is what we had for the vertex form of a, or is what we had for absolute value, which was already in quote-unquote vertex form. Absolute value was written like this when we had all these transformations. We had a times the absolute value of x minus h plus k, where before we said that h was the horizontal movement and this number was a liar, because it did the opposite of what we thought. And then this k is the vertical movement, did exactly what we thought. And this a was our telling us whether it reflected or not vertically, as well as whether or not we stretch it or compress it vertically as well, depending on what we multiply by. And those numbers play all the same roles here, where this is telling us again horizontal movement and is once again a liar. This is telling us vertical movement, and this is telling us whether it's stretching or compressing, or reflecting, or some combination. So here then, knowing that our normal vertex for a quadratic function, if it's f of x equals x squared, for example, is having the vertex at the origin, very similar to an absolute value function. The vertex is typically at the origin for the parent, or is at the origin for the parent function. And then any modifications on that, transformations on that, such as moving it left and right or moving it up and down, move that vertex to where we have our vertex is h comma k. Our vertex is going to be whatever the opposite of this number is, because it's a liar, and whatever this number is for the y value. And then the nice part about this is you know the vertex rather than having to find the vertex. So I love graphing from vertex form for that reason. And so the axis of symmetry, if recall, the axis of symmetry was x equals a number, and it was a vertical line, and that number that it equaled was always the x value of the vertex. Well, since our x value of the vertex is h, it's going to be x equals h. Now remember, this is negative h, which is why we see the opposite here show up, which is why I said that this one's a liar. And then, as we mentioned just a moment ago, a determines the width and direction of the parabola, aka the vertical stretch compression, as well as whether it opens up or down, because whether or not it's reflected or not. Now, why do we want to use vertex form? Well, like I just mentioned, vertex form shows the vertex without having to do a bunch of math in order to find it. And same with the axis of symmetry. We don't have to use x equals negative b over 2a and then plug that number back in to find the y value of the vertex. And so it shows where it is in respect to the parent function, or compared to the parent function, f of x equals x squared. It tells us it moves left and right and up and down a certain amount, telling us it moves from 0, 0 to the new numbers. So now we have these transformations that are written from the parent function, f of x equals x squared. We're supposed to describe how these changed. So this is very similar to what we'd had prior, to where we notice that when the number is adding or subtracting, that's dealing with the translation slide or shift, the moving up, down, left, and right. And when it's inside the parentheses, that's when it's doing the opposite and it's horizontal. When it's outside the parentheses, adding and subtracting, that's going to be dealing with the vertical movement and doing exactly what it says it should. And so on number 1 here, a is 1, and it's positive. So it's not reflecting, it's not stretching, it's not compressing, because a is 1. This plus 9 outside the parentheses, since there are no parentheses, is telling us that it shifts, slides, or translates, any word you want to use there of those three, up 9. Number 2 here is telling us it does the same thing, but instead of going up 9, it still shifts, going down 2. On number 3, it's telling us two different things. This negative tells us it reflects vertically, or reflects over the x-axis, whichever one of those you want to say I'm perfectly fine with. This plus 5 tells us it shifts, and this is horizontal, so it's inside the parentheses. And since it's inside the parentheses, it's also a liar, and so it's going to be left 5, even though it says positive 5. I don't know why I capitalized L and left, but oh well. On number 4, The A is 1, so it doesn't tell us, it doesn't reflect, and it doesn't stretch or compress. But this -4 does tell us it shifts, and so does this -1. And you could list this as two separate bullets, like I did, two separate dashes, or one dash, excuse me, like I will do. But you can say it shifts right 4, because that's a liar for that one, and down 1. Or you could say like shifts right 4, shifts down 1 as two separate dashes. Here, this 1/3 tells us it compresses because the absolute value of 1/3 is less than 1. You multiply something by a third, it gets smaller. So it's going to vertically compress by 1/3. And then this +2 tells us that it stretches, or excuse me, shifts, my apologies, I said the wrong word, shifts up 2. On number 6 here, this -2, the negative tells us one thing and the 2 tells us another. So the negative tells us it reflects vertically or over the x-axis. I'm going to write vertically this time. It's the same thing to reflect vertically as well as reflecting over the x-axis. This 2 tells us it stretches vertically, so it's a vertical stretch by 2. And then this +4 tells us the third thing, that it is shifting, translating, or sliding left 4, because that one's a liar once again, whenever it's with the x. So on number 7 here, we're going the other direction. We're told that Mason graphed the parent function of a quadratic function. Then he reflected it over the parabola, or reflected over the x-axis, okay, vertical, translated it 7 units up and 3 units to the right. And what's this new one? Well, let's go through piece by piece and see what it's telling us. So the reflecting is telling us it made the A negative. This is telling us that we went 7 units up, so that's adding 7 at the end. And 3 units to the right is subtracting 3 inside the parentheses. So we put this in a case. We put this into action. So since we're going to be going left and right, we are going to have our parentheses here. And it's going to have a negative outside the parentheses since it's reflected. Inside the parentheses, we're going to have x -3 since it's moved 3 to the right. And then outside the parentheses, we're going to do +7 since we had 7 units up. And we piece this together part by part of saying, hey, it did this, this, and this. So we listed each one individually as negative, -3, and +7, and included them in our function. Now let's practice graphing here. And when we graph, we're going to follow the exact same steps we followed last lesson when we graphed these quadratics. However, the first couple steps are going to go faster because rather than having to find the axis symmetry in the vertex using x equals -b over 2a and then plugging it back in, we're just given it if you know how to read the vertex form. So we know that since this is -2 and +3, it's going to be 2, 3 for our vertex. So I'm going to do v colon 2, 3, v for vertex. And it does also give the axis symmetry. So remember that the axis symmetry, I abbreviate it as AOS personally, is x equals a number. And it's always x equals the x value of the vertex, 2, the liar version of this number. So I'm going to put that in my table here, 2, 3. And then just like we did before, I'm going to fill in the rest of my table doing increasing and decreasing numbers on the x values. And then I'm going to have to actually plug these in to get the y values out. So I do still have to plug in numbers, but I don't have to plug in my vertex because I already know that one from the form. So as I plug in these y values here, I do have to be careful that I am squaring after I subtract. So for example here, like if you plug in -1, this is going to be -1 minus 2 squared plus 3, which ends up giving us -3 squared plus 3, and -3 squared is +9. So you got to be careful there with your signs and just make sure that you're following PEMDAS for the order of operations, going inside the parentheses first with subtracting 2, and then doing the exponent after that and including the negative as part of -3 times -3. And so you end up getting the y value of 12. And then as I go to my next number, I end up getting the y value of 7, 4, 4, 7, and 12, noticing just like we did last time that the y values are symmetrical, going out from the vertex each direction because this x value of the vertex is halfway between the other x values on each side. So now I'm going to go and plot these points and then connect them on my graph, noting that my y values of 12 go off the graph, and that's fine. We're not asked to give domain and range this time, so we just don't give it. If we were asked to, here the domain is all real numbers, or negative infinity to positive infinity, as it always is with absolute value functions. And the range is 3 to infinity, with the 3 being a bracket because it includes 3, or y is greater than or equal to 3. On to number 9 here. Oopsie. Moved page. This time it didn't do it to me. I did it on accident. The vertex of this, starting there, as well as the axis of symmetry. The vertex is whatever our horizontal movement is. Nothing, adding or subtracting with x inside of a parenthesis, so it's 0 movement on the left and right. But we are moving 4 down, so it's -4. And the axis of symmetry is x equals this number, 0. Put that in the middle of my table. Put numbers corresponding on each side of it, increasing and decreasing. I just choose the next integers, but really you could pick whatever numbers you'd like. As I plug each of these x values in, noting that I plug in -3 being squared in parentheses because this number is negative, and I end up getting the y value out of 5, 0, -3, -3, 0, and 5. As I plot these points, I end up getting the following 7 points on my graph, connecting them, and I have my parabola. And both 8 and 9 had a positive a, so it did open up. It did not reflect vertically and open down. Moving on. Number 10. Here we have a negative, so we do notice that it will reflect and open down. That doesn't affect our vertex or axis symmetry at all, though. So the vertex, the liar, so it's -5, -1, exactly what it says it is. And our axis symmetry is always x equals this number, the x value of the vertex, -5. So in the middle here I have -5, -1, and I'm just going to do increasing and decreasing numbers from there. And as I plug these numbers in, I have to notice that as I plug in, that negative is going to have an effect. So as I do -8 plus 5 quantity squared, for example, I do -8 plus 5 is -3. So I have -3 that I'll square. And as I square -3, I get 9. But this negative very much so is still present. So I have -9 minus 1, leaving me with the y value being -10. As I continue to find my y values, I get -5, -2, the -1 we already know, -2, -5, and -10. And so now I go ahead and plot these points, noting that the y values of -10 go off the graph, and that's perfectly fine by me. It's not a concern that I have. Plotting the other points gives me these 5 points on the graph, and it makes this U shape. Now, I did mention last class how you can sometimes that it might not be a bad idea to do our axis symmetry as a dashed line. If you still want to do that, that's awesome. If not, that's fine. Moving on to number 11 here. The vertex is going to be 4, 0, because this is a -4, so it's a liar, and it's with the x inside the parentheses, and this is a +0 at the end secretly. And our axis of symmetry is x equals 4. And so you could make a dashed line there if you'd like. Not required by any means. Putting 4, 0 in the middle, and then increasing and decreasing from there on each side for my x values. To find the y values, I plug each of these in. And while this 3 didn't have an effect on my vertex, it will have an effect as I plug numbers in, because after I subtract and then square, I will have to multiply the result by 3. So for example, as I plug in the number 1, I get 27 out. Quite large. 2 is 12, 3 is 8, and then I just actually end up having the same exact numbers mirroring on the other way back like we've talked about before. Now, only 3 of these fit on the graph, so I'm only going to graph those 3 and say that's fine by me. And as we can tell, this increases very quickly here. It's really stretched out. That's because it's stretched by a factor of 3. And so you see it going vertically 3 times as fast. Number 12 here. Now we have some piecewise functions, exciting stuff. So I like to make this dashed line here for my split, and they split where it's greater than or less than -2. So I'm going to put my dashed line at x equals -2. Then I'm going to plug in this number here and plug in this number here and go from there. So as I plug in -2 to this first one, I end up getting -1/2 times -2 minus 6. That's f of -2. Equals, I should say. And these -1/2 and -2 reduce, thankfully, and we get +1, and 1 minus 6 is -5. And so I end up having the vertex, or excuse me, not the vertex, but this ordered pair being -2, -5. And that's an open circle because it's not or equal to, it's only less than -2. And this graph will be on the left-hand side of this dashed line because it's less than -2. So I'm going to now say my slope here is -1/2 of this linear equation, noting that this is y equals mx plus b. And this is going to go downhill from left to right. So if I'm going to go to the left, I have to go up. So I go up 1, left 2, up 1, left 2, until I just kind of run out of room. And I draw the arrow because it's going forever, negative, less than -2. As I look at the other part of my graph here, I say, okay, I need to find the vertex. That would be helpful. And so I find the vertex here. I could also start by plugging in -2. Either way is a fine way to start, whether you're starting with the vertex or starting by plugging in -2 is fine. I'm going to start with the vertex here, noting that the vertex is at 1, -5. And so that's going to be one of my points that I have, 1, -5. Closed circle because it's actually part of this because 1 is greater than -2. And I'm going to make a table here just like I did on my piecewise functions last time when I had the quadratic as part of the piecewise function in section 3.4. And I'm going to plug in some numbers including -2. And that's actually the smallest number I'll plug in because it is where we cut off and we don't go anywhere less than -2 there. So I'm going to plug in -2, -1, 0, and I'm going to just plug some in on the other side as well. Oh, I wrote 1 twice, silly me. So as I plug in these numbers and get the y values out, I get the y values out of 4, -1, -4, -4, -1, and 4. Now, -2, 4, it will be an open circle because this is not or equal to -2. So I do have to make sure I do take note of that and make that an open circle, while the rest will be closed circles because they are actually less than, or excuse me, in this case, greater than -2. And we have this curve going forever that direction, but not forever left. And this made our piecewise function, which we could find the domain and range of, and we have before, but we aren't going to do here because we're not asked to. Now, I did not note, but I could have noted that the axis of symmetry here is x equals 1, the x value of the vertex. And I could make a dashed line here as well, but I didn't make a dashed line here this time for the axis of symmetry because I thought it might be confusing with the dashed line that we already did for the piecewise function, showing where we go from one function to the next. And it didn't necessarily require me to say the axis of symmetry. It didn't say, hey, you have to find the axis of symmetry. So you don't necessarily have to write it down in this problem. Whereas on our earlier examples, it said, find it. So we had to find it as part of the answer. Here we have our changing of the functions at 1. So I'm going to make that my dash line. And this top function will be less than or equal to 1, so the left side, or the bottom function is the right side. And I'm going to find my vertex since this is a quadratic function. And this is in vertex form. It also looks like in standard form. It ends up being a little bit of both here because we're moved 0 left and right with the parentheses and 6 up. Now, it would have been purely in standard form if this was like -2x squared plus x plus 6. Then that's no longer vertex form. It's not wanting to undo this. There we go, it eventually went. So the vertex of this one I'm actually going to do it over here because I'll have more room. The vertex of this one is 0, 6 because it's moving 0 up and down, or 0 left and right, and 6 up. And then I'm going to make more points, noting that my axis symmetry is x equals 0 as well, which I don't necessarily have to write down or put on the graph. And I'm going to make a table here, putting 0, 6 in the middle, but noting that it only goes up to 1. It's not going to go up further. So I'm just going to make a few points on the left. I'm going to make more points on the left this time of the vertex because there's more area on the left of the vertex. I could keep going past -2 if I really wanted to, but I'm just going to stop it there. And so as I plug in these different x values, I get the y values out of -2, -4, and +4, 6, and 4. And so I'm going to plot these points, and they're all going to have closed circles because even the 1 is or equal to the inequality there. And so I do closed circles on all of these as I just mentioned. And this goes to the left and down forever, but stops here on the way to the right. As I graph my other one, like usual, I like to plug in this number and see what I get out and make a circle there. In this case, it'll be an open circle because it's not or equal to it. And so I'm going to have -3 times 1 plus 4, and I should note that this is f of 1 that is equal to this. And I end up getting -3 plus 4, which is +1. So I plugged in 1, I got 1 out. So that's the ordered pair, 1, 1. So I'm going to go ahead and plot that with an open circle. And then note my slope is -3 or -3/1 because this is y equals mx plus b. My top one was quadratic, so I graphed it like a quadratic. The bottom one's a linear equation, y equals mx plus b, so I'm going to graph it like that. So I'm going to go down 3, right 1, and now from left to right, this is going downhill. And draw the arrow because it goes forever that direction. Once again, not asked to find the domain range, so we won't be. On 14 and 15, we have inequalities. And just like we talked about with inequalities, it's the exact same as graphing a normal quadratic, except for we have to worry about dashed or solid lines and then shading. So we're also asked to give the vertex and axis symmetry again here. So the vertex on number 14 is 3, 0, because we moved 3 to the right, that's a liar, and 0 up or down. The axis symmetry is x equals whatever the x value of the vertex was, 3. And I can feel free to put a dashed line in here, or I cannot, it's up to you. I'm going to put 3, 0 in my table and put numbers bigger and smaller like I normally do. And as I plug in these different x values, I get the y values out that I am writing currently. So I'm going to go and plot these points, noting as -9 goes off the graph for the y value, and that's okay. Now, as I connect these, I can't use a solid line because this is not or equal to, it's only less than. So I use a dashed line instead. And then the other different part where I shade, I'm going to shade below because this is less than, and these are the y values that are lower than something are the ones that are less than it. And this happens to be kind of inside that parabola in this case, but if it was opening up below, it'd still be below, just not inside. Number 15, same idea here. So we first start off by finding the vertex. And this vertex here, if it wanted to write a v instead of just wrote a straight line, that's neat, as -1, -7. Once again, this being a liar. The axis of symmetry is x equals -1. And I'm going to do numbers that are bigger and smaller again. And as I plug these in, I notice that this is going to stretch quite a bit here as it's being multiplied by 4. And so my y values are going to get big fast, and they do with 29, 9, -3, -7, and then mirroring this exact same ones again. So obviously the 29 won't fit on the graph, and neither does the 9. So I'm just going to graph the 3 points that do fit on this graph. And this does get a solid line here because it is or equal to it. And as we mentioned, it does stretch very quickly, knowing that it would be at -3, 9, so it'd be like up here, for example, for those dots if you were to graph them. Important context. And then these are the y values that are greater than it. So I'm going to do shading above it, which is there. This is technically below, because as it keeps going up, it'll eventually go out, not curving like that, but it'll eventually go out wider and wider as it goes up. And over time would do that. So it can't be below and around, it has to be above in this case. So let's summarize a little bit with this. I should really turn this page. Rotate page. Much better. So now we're going to just kind of recap what we know about quadratic functions. So parent functions, we said the parent function is f of x equals x squared. And we said it creates a U-shape. This graph creates a U-shape called a parabola, spelled parabola. And then we talked about how the axis of symmetry is the vertical line, x equals a number, that divides the parabola into 2 equal parts. And the turning point is called the vertex, and that's either the maximum or minimum, the lowest or highest point. And so if we were to graph this parent function, f of x equals x squared, I was blanking on the word parent function, even though it's, we see it right here, written boldly. Oh well. My x value of the vertex is 0, because it's 0, 0 with the parent function. And then the numbers increasing and decreasing would be as follows. And as I plug these x values in, I get the y values out of 9, 4, 1, 1, 4, 9 with 0 in the middle. And I plot these points, noting that the 9s go off the graph because it accelerates quickly or grows quickly. And I get that graph. Now we're going to talk about how we had standard and vertex form. Standard form was last lesson. Vertex form was this lesson. Standard form is f of x equals ax squared plus bx plus c. And with standard form, we had to find the axis of symmetry by doing x equals negative b over 2 times a. And so we're going to practice that here. And we had to plug it back in to find our vertex. So as I practice it here, I have x equals negative of negative 4 over 2 times 1, which is 4 over 2, or 2. So that's going to be the middle of my table for the x values, increasing and decreasing from there, just like we did before. We had more work to find the axis of symmetry than we did earlier in this lesson. And as I plug these back in to find it, including finding the actual vertex itself, I end up getting 6, negative 1, negative 2, negative 3, negative 2, 1, and 6. So I had to plug this one back in, just like I did all the other x values when we have standard form. So now as I plot these points, I have negative 1, 6, 0, negative 1, negative 2, and I just continue to go along and do all of these points. Oop, I did the wrong one at, no, I did the correct one. I was thinking I made a mistake. Oh, I know what I did here. This should be a positive 1 right here, and I put the wrong thing. So I need to change that. I noticed something wasn't looking right. That looks better. And I graph this. Let me do a little bit less bad of a job on that. Now let's talk about how we do vertex form. So vertex form is f of x, this is what we did earlier in this lesson, equals a times the quantity of x minus h plus k, or a minus h quantity squared plus k. And by earlier in this lesson, I really mean this was this lesson. Here the axis symmetry is x equals h, and the vertex is h comma k, noting that h is a liar for both of those. And so here, we can just know our vertex in this case is negative 1, 6. And we know the axis of symmetry is x equals negative 1. So we're already given these. We don't have to go through the work of finding them like we did with standard form, which is why this is so nice to graph with. When I'm graphing, I really do prefer vertex form because it's very easy to spot the vertex. Now, when you are plugging in the numbers, personally, I do think plugging in numbers into standard form is easier to plug the numbers into, but maybe that's just a personal preference. You know, some of us might prefer plugging it into vertex form instead with these other x values. That really is up to you. So I'll get the y values out here. That'll be writing down now. Negative 12, negative 2, 4, the 6 we already wrote, 4, -2, and -12, noting that the -12s clearly go off the graph. And so I'll go ahead and start graphing these. Connecting them. It does open down since the A is negative. And that's my graph. So you might be wondering, okay, well, if vertex form is so much easier for finding the vertex and we have to do less work with that one for that reason, why does standard form even exist? And standard form is really helpful for finding other things on the quadratic, such as x-intercepts, which is something we're going to be doing a lot of in the future, just not currently in this unit. So we do end up using standard form quite a bit later because it is incredibly helpful for some other things, but vertex form is my preferred form for graphing. And so this is just a nice little summary page of what we have learned so far with quadratic functions, of the parent function, standard form, vertex form, and how we use each. And this wraps up section 3.5 of Algebra 2.